So at least I want you to be very, very thorough as to how the ozone is being formed and what are the responsible radicals, how do they react, and how the HO2 is produced, and how HO2 can transfer the NO into NO2. And apart from that, sometimes, especially if you recall that when we were doing the chemistry of methane, okay, that it can in fact remove NO2 from the system, okay, rather than forming the NO2. And once we are able to form the NO2, then you will likely to form the ozone. And if NO2 becomes too much, then what happens? The NO2 will go to the terminal reaction and form more of HNO3, right? And then that is how it gets out of the system, the HNO3. And maybe we'll discuss a little later, but you should also not forget that the life doesn't end forming the HNO3. Okay, this is the terminal product. But we all know acid itself is highly reactive, okay, and the moment it encounters ammonia, which is there a lot in the atmosphere, we are doing some measurements of ammonia, and maybe we'll talk about few things here and there, and then you'll find is it balance NH4 NH4NO3, okay. And you see this becomes, you started with ammonium nitrate is what it is a salt basically, and then this comes as it's more a heterogeneous equation. It is solid and it makes very fine particles, okay. And then you see we thought that the problem of the particles is not over, but then you see the particles will be formed because of the primary gases which you have in the form of the gas here, G here, okay. And if there is temperatures are very high, okay, then what can happen is this is a reversible reaction, and then you can also form back the ammonia and HNO3. So in daytime you will find NH3 and HNO3 generally larger than nitrogen. Okay, both will be high because of the volatility, and then not only this will be this is situation, but NH4NO3 itself is volatile. Okay, all ammonium nitrate. So if the temperatures are high, you can see the NH4NO3 is evaporated and you don't find the particles. Okay, in the same gas chamber you can see that for a moment there's nothing, all gaseous compounds, and after some time no reaction is happening and the temperature drops and you can see the particles. Okay, so again this is what is the situation. Similarly, if you also have end product, we have not discussed so much, the terminal reaction for SO2 was H2SO4, okay, plus ammonia and H4 SO4, and then of course you have to balance the equation. Okay, how do I balance? 2 nitrogens, okay, 1 nitrogen, 2 nitrogen, okay, 6 plus 2, 8 hydrogen, and the sulfate is sulfate. So you get it without any problem. So again, these are, okay, just imagine, we have the serious problem of the dust in the country, and where is the dust coming from? It's not only the natural dust that comes, this dust the primary origin of these particles, or which we call in the broad sense dust, has come from basically from where this NO3 has come from. It has come from NO2, and this has come from NO, and this has come from SO3 and SO2, right? So where do we make these particles responsible? Okay, they are responsible from the combustion sources. Okay, and that's very important to understand that if you want to control the emissions, or we want to improve the air quality in terms of the particles, in terms of the dust, it is just not, okay, it's just not the particles that you control at the power plant, but you also need to control the gases, which eventually in the atmosphere form the ammonium nitrate and ammonium sulfate, and we have to do some work on that. But what we'll do is maybe we'll discuss a little bit more about those things at some point. But let's get back to something that we were doing in the last class, and I thought it might be a good idea to do a simple example that I was just emphasizing on, that you should learn to these problems as you see them. Okay, you can take this as assignment. Almost I've done it, like 80% I've done that one. You can take that as assignment or an example. Okay, I'm talking arbitrarily about an alkyl, which is for that stands for R, alkyl peroxynitrate, which decomposes in for the peroxy oxide, peroxy radicals. So what you can see is this is two-way reactions. Okay, that the forward direction I'm calling that as K1, and the backward I'm calling as K2. Okay, it breaks down to RO2 and NO2. Okay, this RO2 and RO2 can combine to produce 2RO, and that of oxygen. These are all radicals. You should see there is a little dot here, the dot there, the dot there, and the dot here. Okay, and then it can further decompose the RO, or rather react with NO2 to produce RONO2, not RO2NO2, but RONO2. And then how we are finding the rate constant and rate reactions for this one. So this is a little example. Just assume that RO2NO2, okay, that's because there could be many compounds like this, are decomposing in a chamber. So I do more like a batch study, put everything in the chamber, and put the sensors and continuously measure the concentration with respect to time, right? So we are observing the decomposition of RO2, NO2, and idea is that we want to estimate K1, okay, from the experiment that we are doing. And you can also assume that RO2 and NO2 are at pseudo steady state. Now you have to explain me what is the meaning of pseudo steady state. We have done many problems in the class, or we have discussed what is pseudo steady state condition. Many times, even if it's not steady state, we somehow assumes it to be pseudo steady state, provided it matches with some certain conditions. So now you tell me what is pseudo steady state, because this kind of assumption, this kind of understanding you will require in many kinds of problems that you do. Pseudo steady state is one thing is certain, it's not steady state. Okay, what is pseudo steady state then? Yeah. Try.
Free radicals are for a very short time.
Yes. What it really implies it that not for the short time. What it says is the rate of formation of the whatever thing you are putting at steady state, and its rate of decomposition or rate of degeneration is the same, approximately, like. So then what you are saying is, well, the derivative of this compounds or these radicals or these species with respect to time can be taken as approximately equal to 0, because we are saying that these things are not changing with time. They are constantly generated and constantly degenerated. So we can say, well, this will be at the That's what this pseudo steady state, that this is this. And the second assumption, which is not so bad assumption if you know the theory, then these are the molar quantity of these two things is same. So now what we do with this thing, show that the first order rate constant for this thing, okay, decay is related to, so first order rate constant decay of this is related to fundamental rate constants of the system. What are the fundamental rate constants of system? K2, K3, K4, and the system in the following way, and the way is the, those are the reactions, I write it back for you. So that K you are observing, okay, are related with this. What do you mean by the K observing? What in my reaction, what I am really observing is time, and I am just measuring RO2, NO2 with some time lag, and then I am finding it something like this, okay, some kind of decay, okay. Will it depend fully on K1 only? It will not depend on K1 alone, okay, because why not K1? Because this is also a reversible reaction, and it can also depend on quantity of RO2, right? And RO2 depends on this reaction, and this depends on this. So they all the equations are interlinked. So I can't talk one thing in isolation and they say, well, all right. So I can find out the straight away the rate constant of this one. Okay, the K1 is separate, but what I am observing here is separate. That's what is the important thing that you need to realize. Okay, is this equal to K1? No. Okay, I can find out the slope. I'm sure you must have done dc by dt equals to minus kc. I can just write dc by dt equals to minus kc and find the k. So that k is not equal to k1, but it is combination of k1, k2 and k3. And what is that combination? That is what is thing which you have to derive. Okay. So I've done this one to some extent, okay, to a large extent. So what I want you to write the differential equation for the decay of RO2 NO2. So why don't you try that quickly and see if that matches with the answer that I have. Okay, so that you'll get used to write. The idea is, because you see, I mean, there's hardly anything, because we don't give as many assignments as we should. So maybe you try and you see if you get the same equation or what I'm getting as. Try quickly. I mean, can't give you so much of time, but the reactions are there. I want to write d by dt of okay, I'm sure you all of must have done. So let's open the box. Oops. We have to be in this mode. And here you go. Have I done a reasonable job, or there's an error? There's no error actually. Okay. Just make sure that you understand what I have written is why I have written. Okay. The decomposition of RO2, okay, depends only on what is the concentration of RO2 and what is concentration of RO2 NO2, because the reaction in the reversible direction is possible. So that of RO2 and NO2. All right. So take that as plus K2. I agree with you. So that is what you should take as the plus K2. Okay. All right. If that is done, let's go forward and see. And decay of RO2. Do you want to write that equation for RO2? Should be. I'm sure you all done that. So make sure this is correct. All possible there is an error too, but you should see that this is okay. Now we are talking about decomposition of RO2. That will depend on K1, sure. That will also depend on K2 with negative sign, and that will also depend on K. What should I say here? Okay, that is okay. The square here, right? There has to be square. That's not coming up here. Okay, so this looks all right. Okay. Okay, so we have written this equation, and I'm just wondering if there's anything missing, because okay, K1 is fine. Okay, K1 will be plus for RO2. RO2 disappears through K2 because of this, fine. Plus K3 is again decomposing RO2. That's all, right? Okay, very good. And then what we need to do is something very simple, and of course, what else? What will be this derivative equal to? 0. Okay, once this derivative is 0, I think now it's very easy for you to find out what will be the K observed, and that should relate to this concentration. Okay, try to do that. It's very simple, and then you will get that one. And now the question is, what we wanted to find out was, in the question what we wanted to find out, just see that we wish to for RO2 NO2, right? K1 we wanted to find out, and you see once you got this relationship, okay, how will you find K1? Provided K2, K3 are known. From the study the study we have done in the box, what will we get from here? Because we are only measuring two things, don't forget, time and the concentration of RO2 NO2. So what I'll get from this kind of graph? K observed. Okay, that is the K observed, because this is you are observing the system. Okay, you are observing the system. This is not K1. Okay, that's what I'm trying to tell you again and again, because there is the reaction after reaction. So this is K observed, and the K observed you can put it in here. Okay, and I'm telling you K2, K3 are known. You can find the K1. So that's how sometimes when the relationship, when the equations are interlinked, okay, then you have to account for all those interlinked relationship, and then your interest might be just simply sometimes K observed, but purposefully I said you must estimate K1 so that you can very clearly distinguish between what is K observed and what is K1, and which are different things. Okay, if there is any question, let me know before we go to something else. Okay, then we are back to our the equation that we were discussing last time. Okay, and we very carefully balanced that equation, and I also pointed out to you that it's a terrible mistake if you don't include the nitrogen in the process. Okay, and it's also a terrible mistake if you don't put proper moles of nitrogen. Okay, somebody can say, well, this can cancel with this one. No, we don't cancel them, because what we do is that we deal with the reactants differently. Okay, that is one thing. You look in the isolation, okay, and the products differently in isolation again. And then we also define that if air to fuel ratio, which is observed or actual, if it is more than this thing, then the mixture is a lean mixture for the combustion. Okay, and if it is less than stoichiometric, then we call this mixture is a rich mixture. Okay, that's all we had done. So what I want to do now is do a very simple calculation which you all can understand. Okay, and then you should make sure that you understand that. This is our basic fundamental equation. Okay, suppose I am taking the example of an N-heptane, which is a very one of the hydrocarbons used in the combustion process. Okay, N-hectane, octane are the very common thing. So this is the let's say this is the compound, okay. And why I take this example? Because calculations are easy. This molecular weight is very nicely placed at number 100. Okay. So now this one is, how many moles of this thing is there? 1 mole, correct? Right. So how many moles of oxygen will be required? 11. How? 7 plus 16 by 4, right? That makes it 11. Moles of nitrogen, 3.76 times of 11, correct? You can get the moles, fair enough. You can also get now the mass of the oxygen, okay? 11 times 32, right? That's mass. Okay, you can also get the mass of nitrogen, okay? So now, can you find out the air to fuel ratio? Okay, what is the mass of the air that is entering in? Nitrogen plus oxygen, okay. So that makes it, I'm sure, if it should add to 1510, if not then there's an error, divided by the mass, okay, divided by the mass of the compound that you are burning in, right. So you got this equals to the air to fuel ratio, okay, at stoichiometry for N-heptane. We have found out. Simple calculation. I mean, there's nothing big. We don't talk very big things, okay? Simple thing. So this is what is the equivalence ratio. Fuel to air ratio actual. Then you can find out the equivalence ratio also, okay? This is stoichiometry. So this for this N-heptane, what is fuel air ratio stoichiometry? 15.1. And when you are in the process, then you find out your actual thing, okay? What is your actual ratio? And if your if the equivalence ratio is bigger than 1, then what is mixture is lean or it's rich? That's right, okay. So you understand that. So these are the simple calculations but very important calculations, okay. Let's go down. Oops. Okay. Now I'm writing this equation again because that's really fundamental equation and every time we need to refer to this equation. Now what we are interested sometimes is to know what is, as air pollution engineers or air pollution scientists, well, a combustion engineer will be hugely interested in the things here, okay. What is reacting with what quantity of the you go to a plant and they say, you ask the person operating there, oh, what are you doing? Oh, he'll simply say, I'm maintaining the oxygen level, okay. Well, that's what his job. But you ask an environmental engineer or air pollution engineer, oh, what is that you are observing at? He said, I'm observing the reactants that is going out in the ambient air, okay. So there's a difference in the view as the people see. So let's divide the whole thing between the reactants and the products, okay. And I'm writing them in the molar form, okay. So I can look at the total moles, there's no problem, okay. So many moles of oxygen and so many moles of nitrogen, we know that. Add them up and you find so many moles of reactants, if you like, okay. And let's call that as F, okay. Similarly, I can write the products, okay. Simple job, nothing very hugely difficult. But then you can write this thing and then M, okay. Okay, remember that we are having reactants as F in terms of mole and we are having the as the products in the form of the moles also. That we are calling as M and that we are calling as F, okay. Now we'll come to a little bit of air pollution because maybe the combustion engineers can still talk many things, but okay. Now I want to give an example, okay, how the air pollution engineers want to utilize little knowledge that need from the combustion engineering, not a great deal of knowledge that we need. Suppose, and it really happens, and it's happening all the time, suppose a small fraction, okay, again, and when I say fraction, I'm talking about the molar fraction because we are in the moles, okay, nothing to get confused. Suppose there is a fraction F, okay, of what? Of the hydrocarbon that you are burning escapes unburned, Okay, it didn't take participate, and then there could be many reasons. The temperature was not right, the retention time for reaction to happen was not time, there was not enough turbulence in the system. For the combustion engineering, good combustion, three T's are important. You have to give enough time for reaction to happen. You have to have right amount of turbulence. Okay, so there is a portion T at this is again combustion is surface phenomena. So you have the turbulence. If there is no turbulence, you can't have the proper combustion. And third, and very important, is the temperature. Okay, if you don't have these three T's properly, things go unburnt. Okay. So suppose something went wrong and some fraction of the thing went unburnt. Okay, in spite of supplying stoichiometric oxygen, we supplied the stoichiometric oxygen, and amount of air. Find the concentration of, because now this becomes a pollutant for me, right? So I'm interested what kind of concentration, what kind of emissions of hydrocarbon that will show up in my product, and I as an engineer of air pollution, I'm interested in the product rather than in the reactants. Okay, so that's what we are trying to do. Okay, don't forget F was the reactants and M was the products. Okay, now unburnt hydrocarbon in the exhaust, and the units I am giving is ppm. So this unburnt is F mole into, it's a million thing, parts per million to 10 power 6, and now you have to really figure it out what all is in the exhaust. Okay, one minus F time M. Okay, what was the M? Was the product. Okay, but if this was 0, the product was M. Okay, this thing didn't burn. Okay, so I didn't need this thing. So the product is 1 minus F time M. Fair enough, simple thing. Plus F, the quantity of the unburned fuel that went out, which is very, very small, of course, plus the air that did not react. Air we supplied, but it didn't react. Okay, so how much of the air that did not react will show up as such of the product, as such of those reactants into the product? Okay, so that is F time F. Okay, because this, if, let me tell you, if this was, F was 0, because combustion was complete, this term becomes 0, correct? So this is the term, that is air going out without taking part as such. Okay, otherwise this would be taken care into the M. So this, yes.
M is moles.
Everything is in moles.
F is in moles.
Yes.
So how can you add a fraction and a moles?
And the fraction is in what units?
Fraction will be in.
It's a mole fraction. It's a mole fraction of the hydrocarbon that we are considering. And how much moles of the hydrocarbon we had considered in our example? Please tell me that. Last in the first thing when we are finding out the products and the reactants, 1 mole. CXHY was only 1 in front, so there was 1 mole. So fraction of that 1 mole escaped unburned. Does that answer your question? Okay. All right. If this is what is the situation, and suppose we are taking the same example. Okay, suppose 0.001, F is 0.001. I think this example is for N-heptane only. Then you can see the unburnt, which is of interest to me as an air pollution engineer, could be about 19.2 ppm. Okay, such a small amount went unburnt. Okay, what we are talking about N-heptane. So that this you can do some calculations. Please check that you can understand this well. Okay, take another assignment. Okay, improve or rederive or whatever, improve the expression if concentration is to be reported on dry basis. Many times you want to express the things on a dry basis. Okay? Okay, this you should try. It is not so difficult. What is to be done? Take the water component out from the products. Right? On the dry basis means you are not considering the water component. Okay, we will slightly get more into the combustion now and look at the formation of carbon monoxide. Okay. Okay, let's have a look. We all understand the reactions for the carbon monoxide. It's essentially the formation of CO2, which essentially go back and forth with carbon monoxide. Okay. And then this is a standard equation that we all understand that very well. Okay, and then what are the components we are considering right now? Are the three components: CO, CO2 and oxygen. Okay. Then what happens is this thing, the value of the K is given. Okay, and then I can write K equals 2. Okay, and what I am trying to write here is total, I am assuming the total moles are 1 mole in the system. Okay. So there will be some mole fraction in terms of CO2, some mole fraction in terms of CO, and some mole fraction in terms of oxygen. Okay. 1 mole I am considering. Okay. Suppose I want to write the ratio from this equations, the moles ratio of the moles of oxygen to moles of carbon. Let's write that. I am trying to write in the moles of oxygen. Okay. How many moles of O? You can say basically O. How many moles, if I am considering in CO2, how many moles of O? 2, because this is 2, so this is 2 here. Then in terms of CO, how many moles of oxygen? 1, so there is 1. And in oxygen, okay, there has to be 2. There has to be 2 XO2. Okay, there has to be 2. Okay, and then moles of carbon. How many moles of carbon? Because oxygen is 2. You can say moles of O. Okay, or the mass of O. So because here, if this is, you can see if this is 2, this also has to be 2. There is an error. No, that is different thing. Now I am not looking at the equation. I have a process in which I have the mole fraction of this, mole fraction of this, mole fraction of this. Okay. Suppose I have this. Forget about wherever. Suppose I even take the volume of the air here, and look at this one. Take some fraction of CO2. Out of that, how much will be O2? No, and then for O, 2. Because see here, 2 here. Okay. And then when talking about the C, then I have the 2 species. The carbon here will give me 1 here, and this carbon will give me 1. This is.
Denominator also could be 2 of X.
Why?
2 of X.
No. How many moles of carbon are here? 1, because the subscript is 1 here, and there is 1 here. Okay. So I'll write there will be 1 only, but this is the correction, that this should be 2 XO2. Okay, we understood that. So now I want to find out the concentration of CO in the process. Okay, then how many are known, unknown, that kind of thing here? We have 3 unknown situations: CO2, CO and O, right? And we have the 3 equations. okay, and I can certainly vary alpha and disturb the combustion process if I like. Okay, I can change alpha, I can put in more oxygen, I can put the less oxygen, okay, and as a result my alpha will change. Okay, so let's do that one and see that how this thing, okay, and this thing, okay, because so then what it depends on, whole thing will depend on alpha, and then depends on K, of course, and K depends on what? Temperature. K depends on temperature. So as my temperature will change, so will be my concentration. I don't know how that will change, that we'll figure it out, will change. And so if I change my alpha, okay, if I'm putting the more oxygen, things might different, okay, if I'm putting more carbon, but what is that which is in my hand to operate, C or O? Oxygen generally, by and large. I mean, you're putting the same amount of the fuel, that is fixed. Oxygen is what that in the combustion engineers they will vary the air amount. Okay, so here generally when we think about the alpha, then we are really changing the oxygen. Okay, so if I look at the final thing, see here I have the temperature. Okay, I'm utilizing that knowledge and the alpha, and what I'm trying to look is mole fraction of CO, because that's what I want to say, how CO formation will depend on temperature and alpha. Okay, so what you can see, the alpha was what? O by C ratio. I am supplying more and more of oxygen. What should happen? Combustion should be complete. So I'm supplying more and more of oxygen, okay, and my CO quantity should decrease. And it does decrease, it decreases here and it is here. Okay, but see, if from the same expression, if I am increasing the temperature of my combustion, okay, if I am increasing the temperature of combustion, so this was my mole of, or fraction mole of CO, this mole went up. Okay, you can do this calculation yourself. I increase the temperature even more. Okay, of course the situation is the same, then I am forming more CO. Okay, so again, well, this is a summary here. The temperature is up, the CO is up. Alpha is up, CO is down. Okay, alpha is up means I am putting in the more oxygen. Okay, so you see, I mean, the science, whatever little we learn, is to again apply to a process so that we can, you know, benefit from the science that we learned. Science is not for writing on the board. Science is not for getting good marks alone. I mean, science is not that you are able to show the things very nicely the way I show. Science must be used. Okay, and that's what all the time we do, that science must be used. So if I want to manage CO, I think I should make sure that combustion temperature is low. Okay, and I supply enough amount of oxygen as is seen here. Okay, let's do the next example. Let's look at the formation of NOx. Okay, see, the NOx is very, very interesting thing. It can form through two routes. Okay, one more route that's called instant NOx, but that is very, very small. Okay, so we will not talk about that instant NOx, but we shall talk about the two routes. That is, the first route is a thermal NOx. Okay, and thermal NOx is defined. It is formed during the combustion processes as combustion of all fuels in the region of peak flame temperature. Okay, what happens? You are providing enough oxygen and enough temperature, which we said do not react, but that's not the correct case. They can react and can form the gas. Well, there is certainly a possibility, and good amount of NO can be formed. And NO also forms. Do you know any source of NO other than the combustion? Volcanoes. Other than that? Lightning. It's not very small amount. It is really, it's not small amount. The lightning which happens in the atmosphere, like we just see the lightning and sometimes enjoy or get scared, but the temperatures there become huge. It's so high temperature, then nitrogen oxygen is there anyway, so that reaction produces NO and also sometimes NO2. Could be a significant amount, like. And it happens at higher altitude, so it can affect the chemistry at the higher altitude. Anyway, so what we have said here is that this can be happen in the combustion process, okay, like in presence of heat. This is the atmospheric nitrogen, and this of course is atmospheric thing. Okay, so that is one route. And then this is very much temperature dependent, that we will show you in a moment. So it also depends on the temperature. So you will get, because of the oxygen that you are putting, or let me say, because of the air that you are putting in the combustion process, that will cause the emission of NO. Okay. But there could be another route also. Okay. What is the other route? Fuel NOx. It means the amount of nitrogen that was present in the fuel may burned out as the oxides of nitrogen. Fuel NOx during the oxidation of the nitrogen containing compounds in the fuel. Okay. What you need to see here, the most of the NOx are from the thermal route. Okay. Generally, right? Unless you're talking great deal of nitrogen, presence of nitrogen in the fuel itself. Okay. The most of the NOx are formed through the thermal route. High temperature and high oxygen content favor NO formation, and preventing one or the other condition is the basis for the most control of NOx in the combustion process. So what is important here? Okay, two things. If this reaction is happening, okay, what is the rate limiting in the combustion process? Is it the species which can limit the rate of formation? Is it nitrogen or oxygen? Oxygen. Because nitrogen is in plenty. Okay, 78% is nitrogen. Who cares nitrogen decreasing or increasing? Okay, so rate limiting species is oxygen. Okay, and what is the other rate limiting thing? Is the heat. Okay, so whenever you're talking about the control, talk about O2 and temperature. You should try not to give too much of excess air, and you should also try the temperatures don't go very high if you want to really control the NOx. Okay, and that's what is said here. Okay. Let's look at the same kind of relationship now with respect to what is happening with the NO. This you see equal to NO, okay, and then the K, that is the equilibrium constant, okay, can XNO, that you can see there's no problem with this relationship, right? And I'll send you the slides so that you can see as okay. Same idea, okay, same idea, but this time situation is reverse. Last time we looked at O by C, right? And here I am looking by N by O. There's a reason that I'll explain you. So let's go back and see and try to have a relook what the student asked. That well, the moles of nitrogen here. How many moles of nitrogen here? 1. Okay. How many moles of nitrogen here? 2. How many moles of nitrogen here? Sorry, oxygen. Okay, 1. And this should be again the 2 here. Okay. So that's what you will get. Okay. All right. So again, I can do the similar kind of produce a similar kind of table to show how much NO will produce and how it will depends on, which we are trying to answer, depends on oxygen and the temperature. Okay. So let's quickly look at the. Okay. Now look at the relationship that we got. Okay. We have the beta here, and beta was what?
N by U.
1 by O. Okay, and then what we are finding here is as the temperature is increasing, the formation of NOx or NO, let's not call it. Clear? Okay. And now let's have a look at the beta. Okay. So beta is 4. Okay. When I say the beta is 4, what it really means? That is correct, but in my combustion process, where am I? Okay, where am I in terms of air to fuel ratio? Or I am very, very close to stoichiometry. Okay, what is the ratio of N by O in the atmosphere? 3.76. What is that? 4. So I am very, very close to stoichiometry. So the chances of forming NO is very little. But if I am giving a high temperature, well, the oxygen to be used in the combustion process or burning your hydrocarbon will also have the opportunity to react with the nitrogen because of the high temperature. Okay. But suppose I increase excessively the beta. Okay. If I am increasing excessively beta, am I increasing? Yes. So what am I increasing really? Or increasing or decreasing? This beta will increase because of increase in N or decrease in O? Decrease in O. Okay. So when I am increasing this, okay, so it means when I am increasing beta, it means I am decreasing O. So it means I am supplying less oxygen. So the opportunity of the formation of NOx should reduce. Is it reducing? I am not sure, but let's see. It reduced from 7 to 2. Okay. It reduced from 4 or whatever 0.4 to 1. It reduced from 0.1 to 0.2. Okay. It's just because you see here somebody can argue the beta, well, beta can be manipulated with nitrogen or oxygen. Because nitrogen is anyway there. It is the oxygen that we should really consider because that oxygen is what is primarily responsible for the combustion, and our oxygen quantity that we supply, it depends on the combustion. So if I look at the beta is being 40, it means this quantity has to be, okay. And then you see the effect of the same thing we are talking about, the effect of oxygen and the temperature. More of the excess air that you supply, more is the NO formation. If you are operating your combustion process at a high temperature, then you are likely to produce more NO. Okay. Let's also make the things a little bit more complicated and look the formation of NO2. Okay. And the way the NO2 is formed is, again, this is NO, and it's generally the NO that gets oxidized to NO2. Okay. Right. Then there's two equations. I can write K1, okay, and I can write K2. The expression is available to me, so that you know how to write that. Okay, and then always keep in mind, in the back of mind, both K1 and K2 depends only on the temperature of the combustion. Okay, so that we see it clearly here. Okay, then now I had not the 3 species but the 4 species, NO2, NO, O2 and N2. So the mole fraction of this plus this will be equal to 1 because I am taking them as the mole fraction. I can redefine my beta, okay, redefine my beta again in terms of moles of nitrogen to moles of oxygen, right? Same thing which is here. So now let's see, I have to consider all the species of the nitrogen containing species. 2, 1 and 1. Okay. And now look at the oxygen. 1, 2, and 2. So this is more or less error free. So I can find, I can take the beta, okay, that is this variable. So now what you do here, and now what is my objective is to look at the formation of NO2, okay. So I mean how many unknowns are there? 4, 1, 2, 3, 4, okay, and how many equations I am getting? 1, 1, 2, 3 and 4, okay, and here I am varying the beta. I can vary the beta, and this expression that I'll get for NO2, which is a little complicated, okay, but you can certainly try. I mean, with all the computers, and my NO2 will be function of what? Will be largely function of beta and the temperature, okay. Okay, and then let's have a look onto the situation as to what the picture look like. Okay, that is from the equations, and then once you solve this, okay, and then as I'm taking the same beta 4 and 40, okay, and the same kind of temperature as this one. Certainly, as the temperature increases, more and more, okay, of NO2 will be formed. Clearly seen, because it's simple. More of the NO will be formed, so the more likelihood of NO to be formed. Okay. All right. If I have the excess air, okay, correct, then what happens? Oh, I'm sorry. When I have the deficit in the air, O I'm reducing. I'm sorry. So when I'm reducing, the less oxygen. So it means the formation should reduce from -10 to -11, -6 to 9 to 1, and then from -5 to -6. Okay. If you compare this table of formation or the mole fraction of NO2 vis-a-vis the table that I gave you for NO, what you see in terms of, well, let me complete the question, in terms of the quantities of NO and NO2. You recall what was the NO quantities formed in the mole fraction, if you have written that down? It was something like 0.007, right? If you recall, I can show you that. 0.007 or 0.045, okay? And when I'm looking at NO2, 1/millionth of that one, 10 to the -10, -11, okay? So we conclude there's no possibility or very little possibility of NO2 being formed in the combustion process, okay? And you recall that I had given you, I had kind of explained you that, well, what happens is, I didn't give you the reason that time, but if you'll recall that I did draw this picture, which we'll do it again quickly, is the almost, if you like. There is no possibility of formation of NO2. We proved that, but last time I just gave you this one. Oh, believe me. But now you can very well be sure about this one, because NO2 insignificant. But by the time things travel, the picture changes, and then I have good amount of NO2, and that we have seen how does the NO2 comes in the atmosphere, how it is formed in the atmosphere, okay? Because of ozone and because of the hydrocarbons and other things, there are many ways, there are many people sitting in the atmosphere to oxidize NO into NO2, which our combustion process could not do. And then the NOx can nearly be equal to NO2, okay? Because NO is somewhat insignificant, Don't tell me that you are standing on the roadside, okay, at the GT road, and you say, sir, we did this measurement and you were wrong, that we were largely NO, because you are very close to the vehicle. And then you will, if you are measuring at GT road, okay, then you will find the situation, that also receptor houses are there, but you are very, very close to GT road, you will find mostly NO. You will not find NO2. Okay. So in a way, with the help of the combustion theory and things like that, we could explain as to how and under what condition what will be formed, what will be more, what will be less, and things like that. We also kind of verified the little thing that I had given in the, I don't know, second, third, fourth lecture, and then we can see this. I think we need to stop here. What is the time now? 12? Okay, very good. So that worked out very well. We might still talk about a little bit more NOx in the next class, how to control and things like that.